Let's take a look at what happens when we have two spatial dimensions. So, for example, diffusion in 2D, day phi, day t is equal to the k times the gradient operator squared multiplied by phi. And just recall that in the elliptic form, i.e. steady state, phi squared equals 0 is the same as this, except that it's in the steady state. And so we term it an elliptic equation. Okay, so just remember that your gradient operator, or nabla, is equal to derivative x multiplied by the unit vector I plus the derivative with respect to y multiplied by the unit vector j. Okay, now there are strict stability requirements in this instance. So delta t has to be less than or equal to 1/8 of the grid spacing squared divided by your diffusion coefficient, for example. And for a uniform grid where delta x equals delta y, we have that delta t, or our time step, must be less than or equal to 1/4 of delta x squared over k, or lambda must be less than 1/4. This is an important implication between how halving your grid scale scales the time step that you require to solve the solution. Okay, and implicit methods by themselves in this setup are inefficient to solve. So in general, what happens is we use a splitting method or technique. That is, we split up our grid. So let's say we have something with x and y dimensions. Okay, so this is xi plus 1, xi minus 1, this is yi minus 1, yi plus 1, and this spatial grid is for Tn. We split up our grid, so we use the spatial values along I, say for the y example, and then we move to our halfway between Tn and Tn plus 1. So I'm just going to complete drawing this picture. Okay, and we calculate spatial values along this direction. This is Tn plus a half. And then we move again to, let's make it a bit bigger. Finally, we get to Tn plus 1. So essentially what we do is, so now we've gone in this direction, so now we use this splitting technique. So essentially what we do is we split it, calculate along this direction, move to we split between Tn plus 1 and Tn, we calculate along this spatial dimension, and then we calculate along this spatial dimension. Okay, so let's have a look at a method called the ADI, or the alternating direction implicit method.